So next I am going to talk about another case, another example. So in particular, I have this famous equation given by Schrodinger. So this is another wave equation which tells us, notice that this is now a complex wave because of the presence of this iota. So this is equal to v of x minus h hat square by 2m, so del square of psi. So psi is what we call as my unknown to the problem or wave function, and v is, so typically I have this Schrodinger equation which measures the total energy of a particle given by the sum of this potential energy. So this is the potential function and this is the kinetic energy, the kinetic energy operator. Okay. So just to give you a brief overview of this equation. So suppose then I have this constant h with a cross, it is also known as the Planck's constant, and this has a known value. So if I choose my potential V to be a constant, right. So if my potential V is a constant, then I can find the solution of this example of this wave function of the type of plane waves. So what do I mean by that? Is if I take my V to be constant, I can show that my solution to this Schrodinger equation is of this form. Okay. Now let us look at the solution to this equation with V constant. So I am going to assume that V is constant. So this is going to be assumed and I am going to solve this equation. Okay. So if I were to apply my if I were to choose solutions of this form, so seek solutions of this form, and for that type of solutions I would like to know what is this A, this amplitude A. So if I plug this solution to this equation, this Schrodinger equation with V constant, I get the following expression. So we see that there is an I h cut sitting here, psi of t. So psi of t is going to pull out an negative I omega. So I get negative I omega is equal to V is a constant, minus h cut square by 2m and del square psi. So del square, it's a problem in one dimension. So each derivative of x is going to pull out one ik. So I get ik square. So if I were to simplify, I get this is equal to h hat omega is equal to V plus h hat square k square by 2m. Notice that this is the relation between omega and k. So if I were to choose my solution of this form, omega and k must satisfy this following relation if this function is to be a solution to this equation. Now in particular, this relation or relation to any PDEs in general are also called as the dispersion relation. So when I talk about the PDEs and I transform the PDEs into this Fourier plane, then the corresponding PDE or the corresponding equation that I get in the transformed Fourier plane, Fourier or Fourier Laplace plane, is the so called dispersion relation. So this is identically equal to the PDE in the physical plane or the xt plane. So this is quite common it is quite common by scientists throughout the world to figure out the dispersion relation and compare it with the solution to the PDE and how accurate is the solution. Now, just to give you a bit more highlight, we see that for the dispersion relation, let me write down h hat omega is equal to V plus h hat k square by 2m. So that's my dispersion relation. Now there are some important quantities that can be found out of this dispersion relation. One of them being the so-called group velocity, right? And the other one that is commonly used is the so-called phase velocity. So what is group velocity? Well, mathematically, group velocity is given by the expression del omega del k. So I need to divide throughout by h cut here and differentiate omega with respect to k. So in this case, if I were to find the group velocity, I get that this is equal to h cut k by m, and phase velocity is omega by k, which is in this case, in this scenario, given by V by h cut k plus h cut k by 2m, right? Notice that the group velocity and the phase velocity are two separate quantities. Now let me just give you a little bit of highlight as to what are these quantities. So suppose I am talking about a wave. Let's say I have a wave which is moving with time. So I have a wave. Let's say the wave psi is given by a sine at sine bt. So this is one plane wave. So notice that this wave has two frequencies. Well, one will be, say, let's say A is not equal to B. So in this scenario, there will be two frequencies with which this wave is propagating with time or changing with time. One could be where A is bigger. In that case, we have the slow wave, and when B being smaller, we could have the fast wave. So if I were to plot this expression over this on this graph, I am going to get the following curve. So let us say this is my envelope. So this is my slow wave, this is my the slow frequency evolution, and within that slow frequency I will get the fast evolution of the wave. So the speed of this, so this is the envelope. So the envelope speed, is also known as the group velocity Cg. So I term this as Cg, the group velocity, and the velocity of this one wave packet is also called as the phase velocity. So I denote this by Cp. So the velocity of one wave packet or one particle within that wave is the phase velocity, and the velocity of the entire envelope of these waves is the group velocity. Okay, moving on to the solution. I have the following. So I am solving 1D Schrodinger equation. Just to recap, I am solving 1D Schrodinger equation for free particles. 1D Schrodinger equation for free particle, that is V is identically equal to 0. So what I have is that I have the following equation. So this psi t is equal to negative h cut square by 2m psi xx, where x is from negative infinity to infinity and t is being the time is greater than 0. So let me provide some boundary condition. So psi of x comma 0, let us say, is psi 0 of x, again from x negative infinity to infinity, and psi of x comma t decays to 0 as x goes to infinity. So in the far field the solution decays. So to solve this, if I were to apply the Fourier transform, so apply Fourier transform with respect to the variable x. So I apply Fourier transform with respect to the variable x. So I get the following expression. I get h cut psi of t psi hat, where my psi hat is the Fourier transform of psi. So h cut psi hat t is equal to k square by 2m psi hat. Now after applying the boundary conditions, I get, well, the initial condition, sorry, and the boundary conditions as well, right. I get the solution psi hat of the following form: psi hat 0 of k e to the power negative I alpha k square t, where my factor alpha is h cut by 2m. Notice that as my t goes to infinity, well, at t equal to 0, the solution reduces to the solution given by the initial condition, and as t goes to infinity, we see that the solution decays. So this satisfies all the initial and the boundary conditions. Okay. So then my solution psi of x comma t will be the inverse Fourier transform of psi hat, which will be equal to 1 by square root 2 pi. I am just applying the formula in this case, minus infinity to infinity psi naught hat at k e to the power I k x minus alpha t dk. Okay. So this becomes now, if I were to use the Fourier transform of psi naught hat, this becomes equal to 1 by 2 pi integral minus infinity to infinity e to the power negative I k y psi of, I am going to use a different variable, y comma 0 dy, and then the other integral is this one. So integral from negative infinity to infinity e to the power I k x minus alpha k t dk. Okay. So notice now I have two integrals, one with respect to y, the other with respect to k. So let us now combine these exponential factors and rewrite our expression. So this becomes 1 by 2 pi 0 from integral from minus infinity to infinity psi of y comma 0 dy, and then the other integral from minus infinity to infinity e to the power I k x minus y minus alpha k t dk. So I am going to evaluate the second integral by completing the squares. So I am going to complete squares here. In particular, I have e to the power I k x minus y minus alpha k t is equal to e to the power, let us take out this I alpha t out, this becomes k square minus 2k x minus y divided by 2 alpha t plus x minus y square by 2 alpha t square, and then minus x minus y divided by 2 alpha t whole square, one and the second bracket. So, after completing the square, I am going to see that this is also equal to exponential of negative I e to the power negative I alpha t k minus x minus y divided by 2 alpha t square times exponential I of x minus y square by 4 alpha t. Okay. So, I am ready now. So, this expression is going to be substituted in this integral, and after substituting these values, so let me substitute all the values. I get that psi of x comma t is 1 by 2 pi integral from minus infinity to infinity e to the power I x minus y square by 4 alpha t psi of y comma 0 dy, and then I have another integral from minus infinity to infinity e to the power negative I alpha t zeta square d zeta, where my zeta variable is k minus x minus y by 2 alpha t. And finally, after evaluating this integral, I am going to get the following expression, that this is equal to 1 by 2 pi square root pi by 2 alpha t 1 minus I times integral from minus infinity to infinity e to the power I x minus y square divided by 4 alpha t psi of y comma 0 dy. Okay, and that is the solution to this problem, which is left in the form of one integral depending on whatever this function psi at 0 will be. Okay, then I am going to talk about another short example, that is on the case scenario of linearized shallow water equation. So, specially found in rotating ocean currents. Now, it has been found that if we were to track the velocity of the water waves, on the surface of the ocean, and treating the ocean floor as a two-dimensional surface with the height separately treated as a variable, then I am able to write the equation for these wave motions in the linearized format as follows. So, I have the following equations: ut minus f of v is equal to negative g eta x, vt plus f of u is equal to 0, and eta t plus h of ux is equal to 0. So, where my function f is given by 2 omega sin theta, and this is a constant. I am going to treat it as a constant, and it is in physics, it is also the so called Coriolis parameter. So, these measures the so called Coriolis or the rotating forces, and then eta is my free surface height, and my velocities u and v are my velocities, right. So u and v are my velocities. So then I need also some initial conditions which are given by u of x comma 0 is 0, and I have the same value for v of x comma 0, and then the height eta at x comma 0 is given by this function eta naught times the Heaviside function at a minus mod x. Okay, so this is the equation that we are trying to solve. Now, if we were, let us say that this is my 1, the set of equations is 1. So, I am going to apply Fourier transform to 1. So, applying Fourier transform to 1, I get the following new set of equations. I get du dt. So, remember, all the capital variables are the Fourier transforms of the small variables. So, v is equal to the Fourier transform of small v, and finally, I have E. Let me say that E is the Fourier transform of eta. So, then my equations are the following: f of v is negative g I k e. So, g, f, these are all constants. Then the second equation is dv dt plus f of u is 0, and then de dt is equal to negative I h k u. So, if I were to combine these three ODEs, notice that this is now an ODE, and the initial conditions of the ODEs are u at k comma 0 is the same as v at k comma 0 is 0, and E at k comma 0 is the following transformed function 2 by square root pi eta naught sine ak by k. Okay, so we take the Fourier transform of the initial conditions for E, and that is what we get. So, combining this into a single ODE. So, notice that this set of 3 ODEs I can combine. Specifically, I can take the derivative of E, which will be as a function of the derivative of u. So, d2e dt square will give me a function of with respect to du dt, and du dt could be substituted from this first equation, but it will still be in terms of v. So, we need to take further another derivative of E to give me dv dt, and so that is how we eliminate and come up with a single equation for E, which is given by the following: de dt cube plus omega square de dt is equal to 0, where my omega square is given by the following expression, or this is also equal to f square plus g h square k square. So, omega is a function of k. So, I can solve this ODE, and the solution to this ODE is E of k comma t is a plus b cos kt plus c sin kt. You can check, we can check that this is indeed the solution to this ODE, which satisfies. Now, we must make sure that this solution satisfies these initial conditions. So, in particular, if I take the second derivative of E with respect to t, I get that this is equal to negative I h k du dt, that is from, let us say this is my I, this is my I double I, and this is my triple I. So, from triple I get this expression, but this du dt is equal to, this is equal to negative IHK f of v minus IGKE. Now at t equal to 0, v is 0 and all I am left with is E. So I get that this is equal to negative c square k square E at k comma 0, right. Now which means that if I substitute, this is going to be c square k square square root 2 by pi eta naught sine ak divided by k. So then, so this is one expression that I have got. So if I were to differentiate this, let us say this is my, so what number have I used? So this is my 3, let us say. So if I were to differentiate, 3 with respect to t, I get that d2e dt square, I get that equal to, and let us evaluate it at t equal to 0, I get that equal to a plus b, and that must be equal to the value that I just got, which is also equal to 2 pi square root 2 by pi eta naught sine ak by k. So that is one relation between a and b. Then what I have is another relation is that dE dt, which is given to be negative IKHU. This is coming from our expression I. So this is evaluated at t equal to 0. I get that this is equal to 0 because u is 0. And I get that, again finding dE dt from my expression 3, I get that this is equal to c. So after finding a, b, c in this fashion, I get that my E, my expression E k comma t is given by the following expression. So this is 2 by pi square root eta naught sine ak by k times f square plus c square k square cos kt divided by f square plus c square k square. So then eta, which will be the Fourier inverse of this expression for E, will be given by the inverse transform. So we take the inverse transform 1 by square root 2 pi integral from minus infinity to infinity, then E of k comma t e to the power I k x d. So this is the variable with respect to k. So dk. So once I use this expression, let's say 5, I use this expression 5, I get my answer, and the answer will be only in terms of, so use 5. So use this expression 5 to come up to this answer for eta. Now similarly I can find the expression for u, for v, and so on. So and so on. Well, these are the only two variables which remain. So you can see that this particular example shows us how to calculate the solution to this rotating ocean currents, in which we have linearized the coefficients of the equation using our Fourier transform. Of course, if we know our initial condition, we can exactly solve all these integrals to get an exact analytical expressions for our answer. So in the next lecture, I am going to talk about again another application of Fourier transform, and further moving from there onwards, I am going to talk about Laplace transform. I will introduce Laplace transform, and then I will talk about some properties of Laplace transform and later on we will look at some interesting applications of Laplace transform. Thank you very much.